We're super happy to have Mohammad here, and I'm happy to see he's doing well, and congratulate him again for getting tenure at Stanford, GSB. And Mohammad, really excited for your talk. You have 45 minutes.
Perfect. Thanks, guys, for the invitation. It's so great to see familiar faces over Zoom. So let me start. I'm going to talk about this paper, which has been going through rounds and rounds of revision. I'm very happy with the recent version, so I'm going to share it with you. It's joined with Suraj Manladi, who is now assistant professor at Cornell, and Amin Saberi, who is a computer scientist at Stanford. Okay, let me tell you what's the problem directly without any introduction. You have a social network on N people, like people who live in Sao Paulo, and you have some diffusion model in mind. One simple diffusion model is what we are observing these days with the pandemic. Once someone is informed about something or infected, I mean, I'm using informed and infected interchangeably, then you're going to inform or infect your connections with some probability, and then they're going to infect their friends with some probability, and so on. And now you have a budget of S seeds that you can initially inform a bunch of people in this network. So think of it as a marketing campaign that you want to inform a bunch of people. And the question is, who are the optimal S people? Okay. So and you of course have like N choose S options to pick. Now for a network like this, if I give you 3 seeds, you know which one to pick visually. For this Facebook subnetwork, it's not as easy to do this visually. And in fact, Kempe Klembeck-Tardosh wrote this paper in 2003, which is now like the most influential paper in networks written since 2000, that they proved this problem is NP complete. There have been a lot of applications of this. I'm not going to spend a lot of time, but the most important one for economists is now the diffusion of microfinance, diffusion of agricultural technologies, and the development economics applications of this problem. You go to a village, you want to inform people of the village about some new technology or some financial product. Or there is this new paper by Pascaline, Dupin, Sylvain, Chassagne that they are diffusing this information about child mortality rates. So people have wrong beliefs about that. And the goal is to find the like central people of the village, or the most like centrally located in the network. So when you have this important from an application perspective problem and it's NP complete, the classic approach is to go after heuristics. There are a lot of heuristics. I just listed them here because this might go to on YouTube and people can look at these papers. But the basic premise of all of these measures is that I will give you a computationally feasible method to rank nodes based on some centrality measure. The easiest one is degree centrality, like ranking people based on how many friends they have, period. But you can have eigenvector centrality or other measures of centrality as well. Just to give you a sense of this literature, it's Kempe Klembeck-Tardosh, what's happening to this paper, and it's just like, it's not stopping. People are just writing papers about this problem more and more. And just to conclude this 8,700 literature, I mean, not all of them are directly about this, but if you want to conclude in a paragraph what this literature has reached in like a vast majority of the paper, this last paragraph of diffusion of microfinance would summarize it, that basically this is important to think about centrality. That's the conclusion. And then there are other papers in development economics with the same conclusion. This is about Chinese villages, and this is about Malawian villages and diffusion of agricultural technology. So now where I'm going with this, even these computationally feasible centrality measures need network data. In order to calculate eigenvector centrality, you should know what is your underlying social network. And network data has two issues. One of them is that it's pretty expensive to build network data of like a village of 10,000 people in India. It's like, how the hell you want to construct that network? The second issue is that even if you go and do a survey home by home, it's going to be pretty expensive. Sorry, it's going to be imperfect. Like, you may not find some people, you ask them, who is your friend? That might be an irrelevant network for diffusion of a microfinance product. I may never talk to my friends about microfinance. I might talk to my priest about microfinance or my teachers about microfinance, whatever. So like, just pausing here for a second, honestly, one issue that I have with parts of the network literature is what is the network to begin with is not really well defined. Like, when we are talking about different issues, different networks become relevant. I talked to Philipp and Daniel and Eduardo about economics much more than my parents. Whereas, like, when we talk about this diffusion, like, we look at Facebook data and it's like a social network of all of these people. It's a little bit confusing. What do we mean by network? It becomes especially important when you think about like Indian villages, because we even don't have the Facebook data about Indian villages. We have to go and survey them to find the social network. There are a couple of papers who address this problem. The first paper by the same four co-author of the Diffusion of Microfinance paper, they say, can we identify central nodes by asking a bunch of questions without surveying the whole network? And the second paper says, can I survey 10% of the network? And from that, use some fancy econometrics to back out the whole network structure. What I'm going to do for you here, and what we do in this paper, is just take this approach to extreme. Like, we are theorists, we like extremes. And I'm going to say, what if you don't know anything about network? Okay, so suppose you are completely agnostic with respect to network. And using this intellectual exercise, I'm going to quantify the value of this like going after central nodes. How I'm going to do that? Actually, I like this next two slides because it tells you everything about the paper, and then I can just switch to Philipp. You don't have to see the theory really to know the message of the paper. So I'm going to take Banerjee, Chandra-Sefar, Duflo, and Jackson paper and do a simulation on that paper, something that everyone in this room can do in a few hours. So they have the network data of Indian villages, 75 Indian villages. They went and surveyed the households and asked them, who do you go to church with? From whom you borrow money? Whom do you like talk to the most? And so on. So they have this network data. It's data, there is no model or mathematical assumption here. Then they have a model of diffusion, which works in this way. They say, once someone is informed about microfinance, they either participate or not with some probability P. It's a reduced form version of modeling your decision process. I mean, it's like, you could also have a model in which people maximize some utility. Then participating agents are gonna inform their friends with probability CP. I'm gonna tell you, hey, Daniel, this is a really cool product. And if I do not participate, I'm gonna inform you with probability CN. We expect CP to be more than CN, but they don't impose any assumption on that. They find it by structurally estimating these parameters. And the whole diffusion process stops after CAP-T period. Okay, so I inform Daniel, Daniel informs Philipp, Philipp informs Eduardo, and then like the product becomes irrelevant. So they estimate these parameters using their data. So by the way, what they observe in data is pretty amazing. The data is public, you should go and look. They know who were the seeds, the first people who were informed. And then they followed like the whole diffusion process, like who informed, who participated, and so on. So they estimate these parameters, and these are the numbers they come up with. This CAP-T, by the way, is basically irrelevant because 7 is more than the diameter of the network. So it's like it never becomes binding anyways. But these are the numbers. There's a range. I'm going to show you something that works for the whole range. So what I'm going to do now is to compare a fully agnostic seeding strategy, i.e. random seeding, with what this paper recommends as something that's better than degree and eigenvector centrality and a lot of these measures called diffusion centrality. I'm not going to define it for you, but this is a measure that is between degree centrality and eigenvector centrality. We really don't need to define it very carefully for the message of the paper. So here is the main graph I like to show you. On the x-axis, I have the number of seeds. On the y-axis, I have the total diffusion, total number of people who are informed. Okay, so let's go through this slowly. Let's start with this point. Suppose I have one seed. I'm going to tell you actually what is the meaning of, let me use a pen. I'm going to tell you what is the meaning of this point here. If I have one seed, and I go to all these 75 villages that I have data for and randomly seed someone, okay, this is data, I randomly pick a node and that person is now informed about the existence of microfinance. Now that person is going to participate with probability 24%. If they participate, they're going to inform their neighbors with this probability. If they don't, with this probability, and I'm going to run this diffusion model. And I do this for all 75 villages, each one of them 1,000 times, and look at the average total participation, average total like information diffusion, how many people were eventually informed. This is the number I get, 60. If I do the same thing by picking the most diffusion central node, I get 127. Okay. So this immediately tells you like network targeting significantly helps diffusion by a factor of 2, in fact, more than 2. What this graph already shows you, and that's kind of my goal in this talk, is instead of looking at the y-axis, I want you to look at the x-axis. If I seed 4 people randomly, I'm already doing better than 1% centrally. Okay, which suggests, at least in this example, random with 3 extra seeds. It could be times 3 actually, I mean, because I'm moving from 1 to like 4, so it could be 4 times more. But random with 3 extra seeds is performing better than diffusion central with 1. And well, the rest of the talk, I have like half an hour or so. I'm gonna convince you this is not like random or incidental. This is actually a fundamental property of this diffusion process, that random with a few extra seeds can win from not only diffusion centrality, but also optimal seeding. Cool. I'm gonna show a lot of asymptotic like graph theoretic, like one asymptotic graph theoretic result, but once you do simulations on like development economics papers, the type of numbers you observe are unanimously between 1 to 3 extra seed is enough. Cool. So, and this is not only about the expected diffusion, but also about the whole distribution. So if I look at the CDF of the performance of different seeding strategies, this is like percentage of observation, this one is percent of informed node, random with 1 seed is here, random with 3 seeds is here, the like orange one, random with 5 seeds is this green one, and optimal seeding with 1 is this black one. So random with 3 seeds is winning, like in a first order stochastic dominance fashion from optimal.
Mohammad, can I ask you a question?
Mm-hmm.
Just clarify. So what you're presenting here is you're taking their model, and then you're proposing a way to spread this information, and then you run, say, 1 million or 100,000 simulations, and then this is the distribution that you get from the simulations of their model according to your
exactly.
Okay,
yeah.
good.
It's their model and the network data.
Thank you.
So in the theory part, of course, I'm gonna deviate from this. So what I'm gonna do quickly, I'm gonna compare 2 worlds, like exploiting the network structure, optimally seeding S nodes. So forget all the heuristics for the rest of the talk. I'm gonna focus on the optimum, which is better than all the heuristics. And in a different world, you ignore the network, you seed S plus X agent randomly, and you ask for what value of X random beats the optimum. Theorem 1 is that X is positive. That's amazing. Theorem 2 is that X is small. So this quantifies the value of network data and computational power at the same time, because I'm assuming you also have access to like infinite computational power. And the main result is that for this class of diffusion models that have the independent cascade property, and I will tell you more precisely what I mean. If the diffusion is going to be successful to begin with, then random with a few extra seeds is gonna beat the optimum. And that's what I mean by viral diffusion. And if random cannot beat the optimum, then even optimum cannot spread the information anyways. That would be the finding. And I will precisely state it. That should be the last thing I would show you on top. And this works even for power law networks, by the way. In fact, it works much easier for power law networks than for like Erdős-Rényi homogeneous networks, which is the interesting part, kind of. So I will tell you the model, I will state the main theorem and proof ideas. I won't get to limitations. That's why I have to tell you guys now that there are multiple limitations to the main theorem. I will state, if you change the diffusion model, result will change. If you change the objective function to a speed of diffusion instead of extent of diffusion. And if you want to solve for the problem of vaccination, this one I will get to, it's really cool. Optimal vaccination, actually network information is very important. Optimal, so attacking a network is very easy with random seeding. Defending it is actually requires a lot of network information.
Sorry, can I ask another question?
Mm-hmm.
So is your main takeaway that if computational power is expensive, so it's hard to calculate the optimum, and one or two extra seeds are cheap, then whatever you're proposing is a good way to approach it. Is that what the main conclusion?
It's two comments. That's like basically the main thing. But two comments. One is more than computational power. I'm worried about the network data actually being more expensive than computational power, because in practice we don't use actually optimum. We use these heuristics. So you can say, I don't care about computational power, but you need to steal the network data. And the second one is what I will propose is use as a benchmark is random seeding. I'm not recommending random seeding as a practical, because you can do better than random with some simple tweaks. This is a theoretical way to say that, look, you should not really be worried about all the details of the network structure. And you can use some basic heuristics, and in a way, quantity has a quality all its own. So that's the, yeah, perfect. So here is the model. You have a network, you have n people and a social network. So this is the set of edges, and two people are connected if they exist in the set of edges. I'm going to focus on undirected networks. So meaning that if you're a friend of mine, I'm also a friend of yours. There are some results about directed networks, tweeters of the world in the paper, and you have like some positive number of seeds that you start with. This is the most important slide of the model section, the diffusion model. The great thing about Corona pandemic is that everyone knows this model now. So the way the model works is that at time 0, someone is informed or infected. Then this person has, with probability C, is going to inform his connections. Okay. Now I can assume that this guy has multiple rounds to inform his connections, so not just one shot. Doesn't make any difference for the results. So you may as well like say that this 5-day contingency, 5 days that you're contagious with Corona is one period. So in this case, these two are not realized, but this one is realized. And at time 1, this guy is the newly informed node. So this guy is now turned off, okay? He is not gonna talk to anyone anymore. As I said, you could assume that this happens multiple periods, doesn't make any difference. Now this guy who is the newly informed node is gonna talk to his friends with probability C again. Some of them are realized, some of them are not. Again, the newly informed nodes, who are these two folks now, are going to talk to their friends with probability C. This guy is now the newly informed node who is going to talk to his friends with probability C. This guy is now informed with probability C, and then this guy has a chance to talk to this guy with probability C, but he doesn't, and the diffusion stops. Okay, so there is no cap T anymore. The diffusion continues up to the point that no one has the opportunity to inform anyone. Think of this as the diffusion of a piece of information like the child mortality rate in our city. Or this professor is a great professor, like you should take a class with him in a college campus. Like people inform each other, and once you are informed forever. You're not gonna be like susceptible again, like the corona. So the set of these black nodes is my objective function. Okay, my goal is to find the best place to put these seeds to maximize the expected size of this set of black nodes. These are the people who are informed at the end of the process. Cool. So I'm going to tell you everything about Kempe-Klemmer-Tardosh in one slide. And that's my only slide that has some notation. I have one more. What is a seeding strategy? The seeding strategy takes network as input and how many seeds you have as another input, and produces as output a subset of nodes. Okay, it's a set function. One example is degree, like pick the top S nodes in terms of how many friends they have. Another example is random, just randomly pick S nodes. Now, as a function of this network, how many seeds you have and your seeding strategy, I'm going to define this A of these to be the stochastic set of eventually informed nodes. This is the set of those black nodes in the previous slide, and that is the stochastic. Of course, it's a function of the realization of probability Cs. The expected size of this, I'm going to denote it by little h function. So this is the expected fraction of informed nodes. Okay. So I see that the diffusion continued, and what is the eventual expected fraction of people who are informed? This is the optimization problem that Kempe-Klemmer-Tardosh proved it's NP-complete. In the space of all possible seeding strategies, for a given network and number of seeds, find the best possible seeding strategy to maximize this H function. They basically showed this is equivalent to like some set packing problem, which is NP-complete, so we cannot solve that, we cannot solve this. And then there is another algorithm I'm going to work with. Because I have no idea about how the hell this optimum works, I'm going to work with an algorithm that's better than optimum. And if I can provide a bound for this, I have provided a bound for optimum. And this algorithm says, hey guys, suppose you know exactly the realization of those probability Cs. So there is no stochasticness in who is going to infect whom. Then equipped with this information, I will let you choose the best possible seeds. Okay, is like intellectual exercise clear? I've used like this idea of omniscient in like 3 of my papers so far. I quite like it. This is really cool. When you cannot solve for optimum, you can just make it easier for the planner. So this is what I'm gonna show you theoretically. I'm gonna start with random. I wish I could compare random with what people do in practice, like microfinance people, which they use a heuristic with an imperfect network data, because then I could tell you what is the practical value of going to the field, collecting the network data and using a heuristic. I can't, so I'm gonna say, okay, suppose you have perfect network data and you can solve for the optimum. And in fact, there is no stochasticness in diffusion. So this is the best possible thing anyone could potentially do. And I'm going to show you that the gap between random seeding and omniscient seeding under some conditions is just a few more seeds, which then means everything else is sandwiched in between. Cool. Let's do a little bit of math. By the way, this picture is exactly what I showed you at the beginning. This is like random, optimum, and omniscient. And this is random with 4 more seeds. Cool. To state the theorem, there is the last piece, which is the network model, and that's the part that I'm quite happy with because we generalized the paper substantially using this new network model, which mathematicians of the crowd will like. So there is this model developed by Bella Barabosh in University of Cambridge and his co-authors. And the model is like this. You have, for each node model, you assign a type. And you can have as many types as you like. So type in a college network could be your age, your race, your gender, your nationality, your like measure, and so on and so forth. Then I define a kernel function which maps two types to basically a number, which at the end of the day is a probability. So this says that the probability that a type I agent is connected to a type J agent is something. The great thing about this is that it's so easy to estimate if you give me the network data, right? I can just define types and look at the percentages, period. This could also be an infinite, uncountably infinite number of types. You can have a continuum of types, and then things would change a little bit mathematically, but conceptually it's the same. Now, if you have this model, now I can define another object, which is going to be super important. This object says, let's Kij be the expected type J friends of a type I nodes. Okay, so I have a network, which is, I have a matrix, which is R by R, so type by type. And for each one, I say, what is the expected type J friends, number of type J friends of a type I node? Cool. I form this matrix, and I define its largest eigenvalue. I find its largest eigenvalue. I call it this object over here. Okay, good. That's my network model. Then I'm gonna like define this new objective function. Remember, this H function takes network, number of seeds, and seeding strategy as input. Now I have a network model, so I'm gonna take expected value with respect to the network model. And this H function is defined. What is the definition of it? What is the meaning of it? It's saying that if I draw a random network with this model that we just had, and use seeding strategy F with S seeds, what is the expected fraction of informed nodes?
Mohammad, can you remind us what age is? I remember age.
Yeah, this little h is the expected fraction of informed nodes for a given network. Now I'm taking expected value with respect to my network model, which is a random network formation. So this is the expected fraction of informed nodes for this model of network if you use seeding strategy F with S seeds. That's the objective function. I've taken this expected value with respect to the network. And then I'm gonna define one object, which is if omniscient, which is like the best possible seeding strategy you have, has only one seeds, then what fraction of nodes would be informed as my networks gets larger and larger? And believe me, this is a constant. I can prove it's a constant. Okay, so here's the main theorem. That's perfect time-wise, like less than 30 minutes. If the largest eigenvalue of your types network is more than 1 over C, and remember, C was the probability that if Daniel is informed, he's gonna inform Philipp. So if the largest eigenvalue times C is greater than 1, and if this reminds you of reproduction number in the pandemic being greater than 1 or less than 1, it's not incidental. This is exactly the definition of reproduction number when your network model is like this complex. Then omniscient with only one seed can inform a positive fraction of nodes in the network. So this alpha is positive. So even if I give one seed to the omniscient, a positive fraction of nodes would be informed. And the ratio of random with X extra seeds to omniscient with S seeds exponentially vanishes. Okay, so I made two claims. One is that this alpha is positive. Even one seed is enough to inform a positive fraction as n goes to infinity. And the second claim is, as X increases, the gap between random and omniscient exponentially vanishes. The second part of the theorem says, what if this largest eigenvalue of the types network times C is less than 1? And in that case, even omniscient with any number of, like, constant number of seeds cannot inform a positive fraction of the nodes. Okay, so even omniscient cannot really do much in the state of the world that reproduction number is less than 1. Okay, so this is basically saying that, look, whether or not some diffusion is going to happen is really about your network structure and the fundamental contagiousness, or this, like, infectiousness of the disease. C is the infectiousness. What is the probability that if I'm infected with COVID, I'm going to infect someone? And this is just a fundamental property of the social network structure. So what you do with this like seeding strategy is not really going to change stuff. That's a claim. Any questions about the statement of the theorem? Let me give you a couple of corollaries. One corollary is this familiar Erdős-Rényi random graph. If all types have equal probability to be connected, it's an Erdős-Rényi random graph, right? So the kernel function is like D for everyone. Any two people are connected with probability D over N. I have N nodes. Any two people are connected with probability D over N. So D is the expected number of friends of any node. This is Erdős-Rényi random graph. Translating this theorem to Erdős-Rényi random graph, you see that if the average number of friends times communication probability is more than 1, that is, if in expectation, if I inform Philipp, he's going to inform more than one person in expectation. So he has D friends in expectation, and each one of them is going to be informed with probability C. Then the same thing holds. And if this is less than 1, then even omniscient cannot do much. So the largest eigenvalue of Erdős-Rényi random graph network is just average degree, because I have only one type. The network is 1 by 1. You can do the same thing for power law networks, and same result holds. Let me show you a little bit of the proof ideas, which gives you the intuition, and then I will close. I have like 12 minutes max. So here is like my attempt to show you the proofs in a few minutes. And it's about communication. Okay, this is how it works. Let's do it together. It's fun. So I have this original social network. This is my network of Stanford College undergrads. Now, a different way to think about the diffusion is, suppose there is a God who knows before time moves on who is going to talk to whom. Okay. So this God is gonna toss a coin for each one of these links in the network. With probability C, he's gonna keep them. And with probability 1 minus C, he's gonna kill them. Okay, so I toss a coin for each link between Philipp and Daniel, and then between Eduardo and me. And if it comes positive with probability C, we're gonna talk. And if not, we're not gonna talk. So this God ex ante knows who's going to talk to him. Now I'm going to construct this new network. Why? Because these two people who are connected, but the God knows they're not going to talk or they're not going to contact, the fact that they were connected to begin with is irrelevant. Like, why do I care whether you guys are friends if you're not going to see each other during the contagiously period? Infectiousness is 0. So the only network that matters is this green network. And the God knows that. I mean, we humans don't, but the God knows. Why this is a cool network? Because if any node in any of the connected components of this new communication network is informed, everyone is going to be informed. If I know if this guy is informed, this guy is going to inform or infect all these 3 people. Or if this guy is informed, he's going to inform this guy, and then this guy is going to inform this guy. Cool. That's why if I give S seeds to the omniscient, omniscient is going to put one of the seeds in this largest connected component. But omniscient is pretty smart. He's going to put the second one here. Omniscient exactly observes this network. That's the definition of omniscient. Someone who knows who is going to talk to whom. The second one here, the third one here. So omniscient very carefully picks the top S largest connected components of this new network. Random, however, is going to hit each one of these components with proportional probability to their size. So if I give you the distribution of the sizes of the connected components of this communication network, we are done with the proof. For the omniscient, you just sum the top S. For random, you just take the expected proportional value. That's what these graph theorists did for us, which is this. If the largest eigenvalue is greater than 1 over C, they prove that you will have a giant connected component in your communication network. A constant fraction of nodes are connected. So if any of them is informed, all of them would be informed. And then all other components are pretty small. And if largest eigenvalue is less than 1 over C, all components are small. Okay, so you will never have a large component. And the proof idea, by the way, for this is that if you have any, for example, if you have two components that are size root n, then you can prove that with probability one of these two nodes here would be connected. It's like if they are large enough, the chance that there is no connection between them would be 0. So the only number that works that two components could be separate is log n. It's kind of magical. I find it to be one of the most beautiful mathematical results I've seen, because it says that there is only log n or constant, no other function would do. Cool. Now, why this finishes the proof? Because here, omniscient is gonna hit the giant component, and then everything else is pretty small. Now, random, the probability that I hit the giant component exponentially gets to 1 as I add a few more seeds. Okay, so if this is 50% of the network and I randomly seed 4 nodes, the chance that I hit it is pretty high. And here, even omniscient cannot do much. You would be like a bunch of log n sums, but relative to the total network, it's pretty small. But the ratio could be huge. Okay, so the ratio of random to omniscient with can be very high here, because random may not pick the largest of the small components. Cool. Great. So that's basically the proof idea. Now let me move. I had one slide. Actually, this is funny. I had this slide before having this like general model. This is the last talk I've given in person before the pandemic, and it was in Yale, and Philipp was there. So I was telling people that, look, all of us are going to get COVID. And it was a sad prediction. So there are like some other mathematical tricks I'm not going to go to. Let me show you one example and finish the talk by this, or two examples. One is why the hell this works even for power law, and the idea is this: if I have the most possible like centrally figured network, the star network, and the communication probability is 0.5. And I have 1,000 people around the star, and I have one seed. Then, by the way, Daniel, okay, this used to be Leo Messi. I changed it to Taylor Swift because you are Brazilian. So,
I think Messi is more popular than Taylor Swift in Brazil still, but that's my guess.
Okay, that's a good point. So what is the optimal seeding here? Well, seed the center, and the expected diffusion would be 500. You have 1,000 people around the center, communication probability is 0.5, the expected diffusion is 500. Now, if I randomly seed, I will definitely hit someone here, with probability like 999 to 1,000. This person would inform the center with probability 0.5, and then center informs everyone with probability 0.5. So total diffusion would be 250. So I'm doing terrible by not going after Leo Messi. But if I randomly seed a bunch of people, then the chance that one of them hits the center is going to be exponentially reaching 1 pretty fast. In fact, in this example, 4 extra seeds is enough to beat central seeding, which immediately tells you that what's wrong with this model of diffusion. It's saying that if I inform like 5 friends of Lionel Messi about something, they are with probability 1, Messi would be informed, and then Messi is gonna inform all of his friends. Whereas it's probably reasonable to assume that in many social networks, that's not the case. Like if Messi has 120 million followers, the chance that he listens to every one of them is really, really, really low. And that's kind of my one, like, so the way I look at this paper, going back to Daniel's point, is it's a joint rejection of the model of diffusion that we use for human interactions and the importance of central seeding. If you believe this model of diffusion that we brought from epidemiology to model social interactions is right, then central seeding cannot really matter. You may as well randomly seed or very simple heuristics. And if you believe in your data that random seeding or central seeding was actually super important, or you believe it for any reason, then your model of diffusion should be something else. There is something else is happening. And then there are results for power law, so I'm not gonna go through that. I just want to show you one last thing and then give the stage to Philipp, which is about vaccination. Let me go here. Yeah, that is my last point, which is suppose now I want to change the objective function from diffusion maximization to diffusion minimization by vaccinating people. And the way I'm modeling this is that I have a network and I randomly attack one node in the network. So in this network, I'm almost surely going to hit the leaves, again, because it's a star, I'm randomly attacking. Now, and then I give you 1 seed to vaccinate someone. Then of course, optimal vaccination is gonna vaccinate the center because the diffusion would immediately stop. If I vaccinate people around the center, well, I'm not gonna do any good because vaccination is not contagious. You're not gonna actually vaccinate the center through this. As a result, if you want to beat optimal vaccination, in this example, you need 75% of the nodes to be randomly vaccinated. Like it's like impossible basically to beat. And in general, you can do simulations and show that vaccinating like randomly is gonna do terrible in like power law-ish type of networks. When you have highly central people, you do have to go after them and limit the network data, which is kind of sad because for creating the pandemic, you just need like 5 people in some random city to be infected. And to stop it, you have to vaccinate 90% of the world. That's it. Let me end by this illustration. That's my, so GSP decided that they want to spend some money by giving a little bit of money to an artist and ask the artist to talk to me about this paper and then turn it into an artist. So I had a like 45-minute conversation with an artist, and then she decided this is the right way to think about this paper. And I kind of have it in my office here on the wall.
Very cool. Is that an NFT?
Oh, that's a great point. I should get the NFT. Cool. Thanks, guys, for listening.
Thanks a lot, Mohammad. Eduardo, should we ask questions now? Wait, let's jump into Philipp.
I think
we're running a bit behind on time. I don't know.
Yeah. So I think it's let's go for Philipp and.
Okay. Thank you, Mohammad. That was awesome.
Thank you,
Philipp.
Inviting. Now the more awesome talk is coming.
Philipp, the floor is yours. We're very excited to have Philipp Strack here as well. Please. You're muted. Still muted. Maybe the mic?
Philipp is not mute. It's like there's something with the microphone.
Yeah, I think there's something with the mic. I guess I can ask a question to Mohammad while Philipp is figuring out his mic. So, Mohammad, you did an amazing job first motivating the networks and then showing why the network assumptions are kind of too extreme. One aspect of the results is it has a flavor of non-discounted games in that you only care about the fraction that gets infacted at the end. Do you have a sense of, if you care about timing, right? So we want to infect people early on as well, how your results will change?
Oh, yes.
Can you hear me now?
Yes, we
Perfect.
can hear you perfectly.
Could you allow screen sharing for me?
Yes.
I will tell you later, Daniel.
Yes, thanks. Sorry for the...
No, sorry on my side. I don't
team.
know what Zoom is doing. I just restarted Zoom.
I actually don't know how to push you as one of the co-hosts. Eduardo, do you know?
Do we want to?
I cannot do co-host.
Your host is room 3 SBE.
Room 3, yeah. You can also send me your slides and I'll share and then.
Perfect.
Yeah.
I will do that. Let me do this.
Tem alguém do apoio aí?
Tem sim, Eduardo, Larissa.
Você pode colocar o Philipp como co-host, por favor?
Ele era para estar como co-host, agora está.
Okay.
Okay, Philipp, now you are a co-host.
Oh, perfect. Thank you. Wait, now I have to
Welcome
go to this window. Perfect. Can you see my screen?
Yes.
Yeah.
Sorry for the delay. Thanks a lot for the invitation and the chance to present. So this paper is joint work with Paul Heidrus and Botan Koshegi, and we want to think about the relation between people overestimating themselves and people developing prejudices against other people. And please interrupt me at any moment. So the broad motivation is that there are two patterns in beliefs which we actually see in data which might be socially problematic. The first one is that people tend to be prejudiced about people who don't share their characteristics. And the second one is that there's disagreement in society about who is discriminated against in society. I will show you some evidence, but men and women, different racial groups widely disagree about the degree and against which groups there's discrimination. And that might be bad for society, because if we already disagree about against whom we are discriminating, then it's kind of hard to fix. And so these two patterns are kind of the starting point of what we want to think about. And what we are going to do is we are going to develop a theory which explains these patterns. And the idea is very simple. So we are going to look at an agent who is rational up to some little twist. And I'm going to tell you in a moment the twist. But this agent is observing outcomes in society and he's learning. And the single assumption we are going to make is that this agent is overestimating his or her ability. And he's going to do so stubbornly. And that is going to lead the agent to misinferences about the rest of society. So what is the mechanism? So I think I'm great. And because I'm great, I should be doing very well in society. Now I observe that I'm not doing as well as I think I should be doing. So I need to explain why I'm not doing so well. How do I explain this? I believe that there's discrimination against me. And now if I believe that there's discrimination against me, then I'm also overestimating other people who are similar to me, because the discrimination will affect them as well. And conversely, I'm underestimating people who are very different in characteristics to me. And this is kind of the main mechanism of the paper, and we are exploring that in detail. And it's going to make very sharp predictions about various things, which we think are testable and roughly in line with what we see in data. And the whole paper, we are going to study beliefs. But of course, once we have all these crazy beliefs, that affects our behavior and can lead to conflict in society. If I systematically think there's injustice and discrimination against certain groups, even though it's not there, and we are disagreeing about this, that might create a lot of conflict and tension within a society. But we're intentionally not studying this because we think that understanding beliefs as a first step is kind of the more interesting part, and then one can put a game on top of this where one can study the resulting conflict. Any questions? Okay, so let me tell you what we do. So we're going to propose this new theory which can explain several patterns in the data which current theories of discrimination and are not going to explain, and I'm going to be very specific about which predictions are in line with the theory. Conceptually, we're going to give a mathematical framework which I think does something new, which I haven't seen in a mathematical framework. It tells you, if you give me some person in society, I'm going to tell you what that person believes about society and in which ways it's biased about all aspects of society. So it's a model where the goal is to predict the beliefs of people in society as a function of who they are in society and the composition of society. And we think this is interesting to study as a model because we have a lot of data on what people, depending on their characteristics, believe in society, and that's actually vastly different across people. And we might want to have models which we can fit to that data. So what we methodologically, there's a mathematical thing which might be interesting. So we study kind of high dimensional misspecified learning models as a step, because these beliefs are kind of high dimensional.
Philipp?
Yes.
Is it that there is a sort of unambiguous notion of position in society, or is that itself a function of people's beliefs or the distribution of beliefs in society?
That's a good question. So for us, we are going to take this as exogenous. So the characteristics in society which people consider being relevant is going to be an input into the model. But I think in reality, this might be determined somewhat in equilibrium. And I think that's an interesting question to study. But we are going to take this as given. And I think there's a lot of follow-up questions this model naturally leads itself to, which we are not going to answer. It's going to be a bit disappointing. But yes, I think that's a question which I think is interesting and I would like to study. Let me maybe be a bit more precise also what I mean by society. So every person is kind of encoded as a string with characteristics. Let's say its abilities, age, gender, ethnicity, education, religion, and also perceptions about competing groups and potentially true discrimination. So all these informations describe society. And this is what we are going to put as an input into the model. And what we want to predict is for each person in society, what they think about the ability of everyone else in society and how much discrimination there is against various characteristics and groups. So we are going to take this very kind of rich description of society and going to output what every person believes. Yeah. And you can use this actually to reason about other biases. We are studying kind of overconfidence, but the mathematical model is suitable to study other biases. Let me briefly tell you about the literature. So there's a large literature on misspecified learning. And what mainly sets us apart is that in this literature, people study how your own actions might kind of confuse you and reinforce misspecifications. But typically, these models have kind of a low dimensional belief space. What is different here is that there are no actions. Information is just going to be exogenous, but we're interested in this high dimensional learning environment. There's a literature in economics and sociology on prejudice and group bias. And I'm going to give you references to this literature throughout the talk. In economics, there's a literature on statistical discrimination. So that's one explanation of discrimination, which we've been using in economics. And the explanation is an equilibrium effect. So I think people with characteristic X behave differently from people who don't have that characteristic. So I treat them differently, and that's incentivizing them to behave differently. And so that's how we sustain this in equilibrium. Note that this statistical discrimination is rational. And I'm going to show you evidence that a lot of beliefs are not rational. And I'm going to be more precise on how to disentangle these different explanations. Another explanation proposed by Becker is taste-based discrimination. So I discriminate against people because I don't like them. And you can test this actually, because if you just don't like certain groups of people, then providing information about these people should have no effect. And the typical rejection of this theory is that we can provide information which changes the patterns of discrimination. And so these two theories kind of have difficulties explaining various patterns, and I will be more precise about this later. And finally, this is kind of a novel reason why overconfidence matters, because it can distort your views of the world. Okay, any questions? Let me give you an example, and this example, then I think you already get kind of the main mechanism, and it's very simple. So let's say you have two people, Alice and Bob, and they have the same ability of 5. But Bob, for some reason, believes dogmatically to have ability 6. And so Alice and Bob produce output, which is equal to their ability minus theta plus some IID random noise. And theta here measures the extent to which there's discrimination against women. So it decreases Alice's output and it increases Bob's output. So suppose when we hire someone, if there's discrimination, then fixing abilities, we are going to kind of promote Bob with higher probability. So Bob believes his output is 6 plus theta plus some random noise. And now suppose that there's a signal about how much discrimination there is in society, which is unbiased. So it's just theta plus some IID noise. And Bob observes Alice's output, like how successful Alice is in society, how successful he himself is in society, as well as these unbiased signals about the extent to which there's discrimination in society. What Bob wants to learn is what is Alice's ability, whether there's discrimination against women in society. And Bob tries to really give his best to learn here. So what we are going to kind of assume is that the noise is IID standard normal, uncorrelated. And this is in some sense an ideal case for learning, in the sense that Bob gets unbiased signals both about Alice's ability as well as about the extent to which there's discrimination in society. So Bob observes completely unbiased signals about both discrimination and ability of Alice, which are the two things he cares about. However, what's going to happen here is that Bob is going to underestimate the extent to which there's discrimination against women by 1/2. And as a consequence of that, also is going to underestimate Alice's ability by 1/2. And the logic of this is quite simple. Bob thinks his ability is higher than it is, so he faces kind of disappointingly low outcomes. He has to explain where these disappointingly low outcomes come from, and he does so by just underestimating discrimination against women. And then this kind of misconception about discrimination leads to a misconception about Alice's ability. And so this is in a nutshell the main mechanism which we are going to study.
So just to clarify,
Yes.
So Bob is going to be computing his posterior using an intercept of 6. Is that what's happening?
Yeah, so let me be more formal, and I wanted to do this in a second, but so Bob is perfectly Bayesian, but in his support of his prior beliefs, they're only data generating processes where his ability equals 6.
Right.
And he's going to update according to Bayes' rule. And this is a statement here about the limits points of his Bayesian updating process.
Under the true data generating process.
Exactly. So he misunderstands the word, but we study the limit points of his learning under the true data generating process. Yeah, that's an excellent question. So what will he believe about the world, about the true world in the long run, given his misconceptions about himself? Let me just make this mathematically formal now. So just to follow up on your question, I'm going to give you a formal result, and then I'm going to forget about all formalities. So suppose there's a fixed vector of fundamentals in RL, and in each period you see a signal, which is some linear transformation of that fundamental plus some IID noise. And let's assume that the linear transformation has full rank. And let's assume that the noise is normal, but potentially correlated in some way. And let's suppose that beliefs are updated using Bayes' rule for some prior P naught, and you update both about the correlation structure as well as about the fundamental. And now the only non-rational assumption is that the agent dogmatically believes that one dimension of the fundamental equals to some fixed number. Formally, that means that all the support of the prior pi naught only includes f comma sigma pairs where fi equals fi tilde. You can now ask, what are the agent's long-run beliefs under the true data generating process? And this theorem tells you the answer. It's not important what the formula is, but the important point here is that you can find a formula exactly telling you what these long-run beliefs are. And there's three different scenarios. So in any case, the agent is going to believe in a single data generating process in the long run. And if the agent believes to know the correlation structure and only wants to learn about the fundamental, you get some formula, and you similarly get formulas for the other cases where the agent believes to know the fundamental and wants to learn about the correlation structure, or the agent is uncertain about both. And this is kind of the mathematical building block for the rest of the paper, and I'm going to forget about it and now just going to talk about long-run beliefs. And these are kind of the unique limit points of the learning dynamics of the agent under the assumptions I've stated. Is that clear? Maybe before I forget about it, because this is kind of the main mathematical point of the paper, I just tell you briefly how to prove this and what's known. So Berg 1966 shows that the beliefs in such a misspecified Bayesian learning model concentrate on the set of Kullback-Leibler minimizers. And we made this normal noise assumption, which very conveniently gives us a closed form for the Kullback-Leibler divergence. And so we just have to minimize this function. And this is sounds a little bit easier than it is, because you have to minimize over positive semi-definite matrices sigma hat. And that's kind of a not so nice minimization problem. And also in the objective, the trace as well as the determinant shows up. But there's a literature in kind of mathematics dealing with this, which is semi-definite programming, and you can use tools from there to essentially solve this problem. And the method is essentially some type of guess and verify method. You relax the problem, and then in the end, you show that something can be achieved. Okay, so now I'm going to go back to the economic model of social inferences. And I first give you the model of society we are going to study. So there are I individuals in society. Each person has an ability, AI, and a subjective belief about their own ability, AI tilde. And furthermore, each person has an observable vector of characteristics. Each entry of these characteristics is either 1, 0, or -1. And these characteristics correspond to K groups, and they can capture age, gender, ethnicity, education, what you're interested in. And so an entry is 1 if you're a member of the group. Let's say you're male. It's 0 if you're neutral to the group, and it's -1 if you're frequently competing with members of this group. And we have a parameter theta k, which captures the discrimination in favor of group K and against all competing groups. And what we want to capture here is that, let's say there are 2 people up for promotion, and then there's just a structural discrimination in society against one of these groups. This makes it more likely for the competing person to be promoted. And so this parameter captures the extent to which we have discrimination against certain groups in society. And each agent repeatedly observes a signal about each other person, which is that person's ability plus the extent or the sum of all the discrimination terms plus IID noise. And the person also observes an unbiased signal about the extent to which there's discrimination against any group. So this is a direct generalization of the 2 people example, but now we have more characteristics than male-female, but we have this whole vector, and we again get unbiased signals. Let me make a few comments. So we think of these concepts as being quite broad. So for example, you can think of A as ability, deservingness, like essentially how well you should be doing in society or how well you think you should be doing. And Q is the achievement, how successful you are in society. And the key assumption we are making throughout the paper is that you kind of are stubbornly overconfident in your ability or deservingness, which is, there's a ton of evidence for this assumption. And we are going to study the consequences and not why that is that you think you're more deserving than other people you think you are deserving. Yes. And we give a micro foundation in the paper such that if you have a biased learning process where you are more likely to remember when you did well, this will cause you to be biased about your own ability and then lead to all these consequences. And that's the mechanism many psychologists think is the plausible mechanism from where this overconfidence comes from. One thing which is important, what we are not assuming is that there's no discrimination. So all our terms are relative to true discrimination. Any questions? Okay, so let me give you our first main result. So this result characterizes the extent to which people are biased about discrimination in society and the ability of other people. So what it says is that in the long run, group K will have the following bias, and person I's belief about the ability of person J will have this bias, and I'm going to decompose these terms and discuss them in a little bit more detail in the next slides. But what the model does is it gives you precise prediction depending on the characteristics of person I and person J of what person I is thinking. So the first term here is, and what is kind of interesting, all these biases scale in the extent to which person is overconfident. So if person I is not overconfident, then this is 0, and in fact, there's no, person I is not going to be biased. That just corresponds to the rational learning case. Excuse me. So let's go through these formulas. So if you look at this formula, then what you see here is that person I kind of underestimates the extent of positive discrimination in favor of group K if CIK is equal to 1. So if person I is a member of group K. So you're going to underestimate the extent to which groups you are a member of are being favored in society. So if you're a member of a group and there's positive discrimination in favor of that group, you're going to kind of underestimate the extent of positive discrimination. Conversely, you're going to overestimate the extent of negative discrimination against those groups you're a member of. Similarly, if you're competing with people from another group, then you're going to underestimate how much these people are disfavored by discrimination. And the intuition is that, again, person I feels he's not achieving as much as he should, and believing in this discrimination explains this perceived injustice.
Philipp, can I ask you a question?
Yes.
Which may not be the optimal timing to ask, but so the mechanism here reminds me a lot of Glenn Ellison's QR theory of slowdown in publishing and over-optimism. I don't know if you remember that paper. It's a paper where everyone thinks that their paper is a little bit better than what it is. And because of that, they assume that publishing requires a lot more supplementary appendices and work on irrelevant things. But so, and he also assumes that people update, like they stick to their biased view, but they don't do Bayesian updating. What he does is some loss, they minimize some quadratic loss or something. So am I incorrect in interpreting what you're doing by embedding this in a fully Bayesian model with misspecified model? And having your setting is a little more complicated because you have these two categories, whereas his paper is just it's me versus the world, right? I think I'm a little better than everyone else, and that's why.
So I should look at this paper. It's actually, I didn't know about it, so I should look at it definitely. From your description.
It's a JPE paper using data from actual journals. It's a similar story, but the model is very different.
So
and it's not Bayesian, yeah.
It sounds to me that the two differences are non-Bayesian and that we are kind of modeling this whole society. But I'll need to look at it. Thanks a lot for pointing it out.
You're welcome.
Any other questions? Okay, let me just, so one prediction by this is that you view discrimination against groups you are a member of then worse than other people will view discrimination against that group. And that makes a prediction of disagreement about the extent of discrimination in society. So this kind of very simple model explains why we are disagreeing about discrimination in society. And let me just give you a little bit of evidence that there's disagreement, for example, between Blacks and other racial groups about the extent to which Blacks are discriminated in the US. The same is true about men and women. And you typically find huge gaps in stated discrimination depending on whether you're a member of the group or you're not a member of the group. And you can find even surveys where whites think that there's more discrimination against whites than Blacks in the US. And so but the kind of conceptual point is that for both statistical discrimination as well as taste-based discrimination, this is very hard to explain. Because in statistical discrimination, we should have correct beliefs and we should not be disagreeing on things. And in taste-based discrimination, just beliefs don't play any role. So the pure fact that we are disagreeing is kind of an interesting challenge for these theories. And we think this is a kind of very parsimonious explanation for why we are disagreeing about the extent to which there's discrimination against my groups. Let me go on a little bit. So a second, now let's think about what person I thinks about person J. And the belief person I has about J's ability is J's true ability plus Sij, which is a measure of similarity times the extent to which person I is biased about herself. And Sij is something which we kind of termed information weighted similarity. It increases in the number of groups I share with person J. So if we have many characteristics in common, then Sij will be larger. And if we have more common competing groups, then it will also be larger. It will be smaller if we are competing with each other. So if I'm competing with person J, then I will perceive person J as less similar. And an interesting feature of this is that if I overestimate person J, then the model predicts that also person J overestimates me. And so these are, I think, quite sharp predictions about what types of beliefs people will hold and in which way they will be biased about each other. And they're kind of in line with something from the sociology literature, which is called in-group bias. So you tend to overestimate people the more similar they are to you. And this is something which the model produces very directly. It also makes another prediction, which is biased reciprocity, that if I'm overestimating you, you're most likely overestimating me. And that's, I think, a testable prediction for which we couldn't find that much evidence either way. But we think that's very much a testable prediction. And for in-group bias, there's kind of a large literature in sociology starting from Sumner 1906 documenting the effect that you overestimate people who tend to be similar to you. And just to come back to the point I made previously, it is hard for other theories of discrimination in which, in some sense, beliefs are either correct or play no role to explain these biases in beliefs, which we commonly find in surveys. And one thing I want to point out that this makes very specific predictions about in which direction beliefs are biased. It's not that it just says beliefs are biased, but we make very specific testable predictions. And in some sense, it blends statistical and taste-based discrimination because if interacting with higher ability people is beneficial to me, then by the fact that I'm now underestimating people who are dissimilar to me, then I will not like interacting with them. So kind of endogenously through this misspecified beliefs channel, I will behave as if I dislike people who are not similar to me. So kind of it's endogenously producing a preference for similar people through the misspecified beliefs. One way how one could test this is that additional information will make very different predictions from taste-based discrimination. Let me maybe go on and give you a few more implications. And I don't know how I'm doing on time. I have 10 minutes?
Yeah, about 12 minutes.
Ah, perfect. So one prediction by the model is that people who are more overconfident should also be more biased. And that's also a very sharp prediction. And this is kind of in line with evidence from psychology that narcissistic individuals who tend to be much more overconfident are also more prejudiced. So there's, I mean, it's purely correlational, but there's a correlation between how much you overestimate yourself and how prejudiced you are against other groups and people. And that's something.
Can I ask you another question? Sorry.
Yes, please.
So these are really cool results. And I'm thinking here, the sort of information you get, the sort of structure you get information about should really affect the bias you get at the end, right? So if I'm working with people that are similar to me, then at the end, right? So they're all similar, but I overestimate myself in the beginning, which means at the end, I should all have a very negative view of all my coworkers at the end. Because I see a signal of our joint production, right? So in order to explain our success and failure rates, the only way to accommodate this, if I'm overconfident about my own skills, is that everyone else is an idiot.
Yep. And so I think that's exactly right, what the model is producing for kind of these co-worker relationships. We explored this a bit in another paper, and I think there are now I think 3 or 4 lab experiments testing this. And I don't know how close the results are to the findings, but you're exactly right about this prediction. And I think where we are going a little bit, if we have time, is to kind of think about how changes in information are going to affect what you believe and against whom you're discriminating. That will be the next slides. One thing which is interesting about this model, and I mean maybe speaks to ideas around affirmative actions, is that the basic fact that you perceive groups as relevant creates discrimination in this model. So suppose you don't think in terms of groups at all, then you're not having any biases in this model because you're not gonna kind of load on the fact that there's discrimination against these groups. You just think of them as irrelevant. Once you start thinking in terms of groups, people will start developing biases in this model. So making groups a salient feature or characteristics a salient feature of the environment is actually itself creating biases in this model.
I'm not sure I understand that, because you assume that you're I'm overconfident with probability 1, right? I'm going to be persistently overconfident.
But the
So what does
question
he
is
mean
whether
by
you try to explain this by believing in discrimination against certain groups.
Ah, okay.
So suppose you don't believe that groups are relevant, let's say your gender is relevant, then you will not believe that there's discrimination against males. And so then you're not going to be biased. But the more salient I make the point that there might be discrimination based on gender, the more I will believe in discrimination against based on gender, and the more biased I will be about the other gender in this model.
I understand.
So making characteristics salient is something which is very harmful potentially in this model. And we couldn't find any evidence on this. What we found is some indirect thing, which is that what many people believe is that an important part of nation building is to kind of de-emphasize tribes. So to create a nation, it's very important to get people not to think in terms of tribes and to kind of indoctrinate them in school so they stop doing that. And there's a hypothesis that that's very important because that reduces conflict within the new nation. And that these explanations are very much in line with this. Yes. So another prediction of the model is the fact that you think of other people as competitors already is lowering your opinion of them. And this is something which is tested in a sociology theory, which is called group conflict theory. And the evidence is mostly along the lines that if you believe that you're more competing with people from a different racial group, then you kind of think less of that racial group. Let me maybe talk about information, which goes back to your question, Daniel. So information can have various effects in this model. So if you learn more about the outcomes of other people, parameterized here in reducing the variance of the noise, this has no effect on your biases. And the reason is that intuitive, we are already in the long run limit. This is not changing anything. If you learn more about your own outcomes, that in fact will make you more biased, because now, given that you get more precise information, bad luck just becomes a worse explanation for what's happening to you. So you will be believing more in discrimination. So the more vague it is how your outcomes are determined in society, the less biased you will be. If you learn more about how much discrimination there is against group K, so suppose I kind of provide objective information about the extent to which group K is discriminated, then this will in fact be efficient in the sense that it reduces how much you are biased about the belief in discrimination against group K. So this information really has an effect, and it will also decrease your total bias regarding discrimination on all dimensions, but it will in fact increase the bias in discrimination about all other groups. Let me just explain this with a very brief example. So there's a bias substitution effect. So suppose I'm a male white university professor and I learn that there's no discrimination against men. And I believe that information. Now I'm going to believe more in discrimination against whites. The reason is very simple. I cannot now explain my outcomes anymore by believing in discrimination against men. So I need a different explanation. So I now believe more in the alternative explanation that I'm discriminated because I'm white. So informational interventions are kind of redistributing biases in this model, and it makes a prediction about why these interventions might not be so efficient. Also, changes in the environment can lead to this type of reallocation of biases. For example, suppose a new social group arrives that's commonly competing with all existing groups, let's say a new inflow of immigrants. And we know very little about this group because they are just new to society and we don't know a lot about their ability. Then it will happen that all agents are going to view this group overly negative, but in fact it reduces biases on all other groups. And there is an example of this, which is, I think, relatively well documented, that when Blacks arrived to northern US cities, this in fact led to fewer biases against Irish and Italians. It's kind of an interesting effect that this new competing group arriving changed the biases between already existing groups in society. Let me maybe do one extension. You could ask, what's the effect of personal contact here? So now, instead of only seeing signals which are distorted by discrimination, maybe I can see signals which are directly about ability. And this is indeed helpful. So in this model, personal contact will lower your biases against that groups. And this is a hypothesis in sociology that kind of personal contact is in general helpful. Yep. And let me maybe not go into detail about this and just skip to the conclusion. So I'm not going over time. So what did I do? So we presented a model of long-run beliefs in a high-dimensional misspecified learning model. We used this mathematical result to solve a framework to think about biases of individuals in society. And what we found in this framework is that overconfidence and the prejudice coming from it through rational learning can actually explain kind of patterns in the data which are hard to explain for other theories. And some remarks is that this is actually very testable in the sense that it makes very specific predictions about comparative statics on how information changes biases. And it's in line with some evidence. And just to state something obvious, we are of course not explaining all social biases. And we think of this as a complement to statistical or taste-based discrimination, which can explain commonly observed patterns and beliefs. Let me maybe conclude here. Thank you.
Thanks a lot, Philipp. Thank you, Mohammad, as well. I don't know how we're doing on time. So, Mohammad, do you want to talk offline, or do you want to answer the question that I left for you when Philipp was offline?
Yeah. If you want to formally call it a day, we can, and then I can tell you about it, or we can.
Eduardo, do you want to call it a day, or?
Yeah, I think
formally.
I'm happy to stay here too. So
let's give Mohammad 2 minutes to answer the question, otherwise it's unfair.
Yes, I even have a picture to show you in principle, but so if you, by the way, Philipp, thank you. This was fun. This was
yeah.
It's always nice.
Both of you.
It's always nice to see Philipp presenting. It's kind of like meditation. It's calm. So if you think about that star example I told you, suppose you only care about the first immediate diffusion, first period diffusion. Then the star example that I showed you, if you hit the leaves, then they would inform the center in one period. And then the center would inform others. So in the first period, you're totally screwed.
Right.
So if you have a high discount factor, then going after very central people, even with that example, becomes important. And then you can go further than that and prove results that we have a couple of results that basically for sufficient, there is this non-monotonic relationship between the two. The higher the discount factor, the more important central seeding. Basically, that's the case. But if you are fine, but the way I think is that if you really care about immediate diffusion, in a very fast pace, you are not really going for viral diffusion. You are going for kind of what I call broadcast, which is different from viral diffusion. You want some influencer to inform a lot of people immediately, and that's kind of advertising more than the broadcast advertising, more than let's make this a viral product. But yeah, so speed definitely changes the things, the results. That's a great point.
Well, thank you both for presenting and sharing your knowledge with us. I hope to see you in person soon.
Yeah, thanks a lot.
And thank you, Daniel, for putting this together.
See you guys soon.
Thank you.
Bye-bye.
Thanks, everyone. Good to see you.
Nice to see you guys.